Very good day and very good morning to everyone and wonderful day to all of you. I am from Group 2 EPD332 Tooling Design from University Science Malaysia School of Mechanical Engineering. Today we will present a project about how to fabricate an internal core from an oil filter from a car. Now let me and my team start our presentation. First, this is the initial process of the production of the internal core of the oil filter. First, the process is similarly the first one is the perforating and blanking process, which perforate and blanks out the desired workpiece from a larger stock. And next, there is the hemming of the both ends of the piece, and then there were the two bending processes, where the two bending processes are mainly done by hand for it to be easier to be fitted into a sealing process. This initial process can be referred as the old production process, and we have some innovation for the process and change some of the process. First, this is the new process that we have changed. First of all, the perforating and blanking is still maintained from the last initial process, as the perforating and blanking is very important and it will be almost same across all other possible processes, as it will perforate and branch out the piece from a larger stock, which is very essential. The next process, we have changed it to a roll bending instead of the hemming and the two bending processes. A roll bending can produce a very accurate result and it is very efficient as well. And the last one, we use a clinching process to join the end of two pieces instead of seaming. And we also didn't consider to use other fastener or other tools or like weldings for the joining, and we chose clinching because it is very efficient, cost effective also, and it doesn't require much energy and doesn't require any other foreign materials. Next, we will bring in one by one. First of all is the perforating and blanking process. From here, we can see the 2D drawings of our design as well as the 3D model of our design. In the next part, in the next slide, you can see the animation of the perforating and blanking process in this work. Let's have a look. This is the initial raw material before the perforating and blanking process, which is just an aluminum roll. And after the perforating and blanking, it has become a small piece of aluminum piece and with all the holes on it. While we design the machine, we have included quite a lot of features into the design of the equipment. First is we consider all the die clearance, which we use is the 15% thickness of the material under the 2.49mm. And as we can see, there is a sliding joint between the dies and other parts. So we also consider the tolerance between the sliding feet of the shaft and hole of the equipment. And we use a tolerance of the shaft has a negative 0.017mm and the hole has a additional of 0.125mm of tolerance. Next, from the working bench, you can see that the side is slightly extruded, so it is to prevent the material from being tilted while loading the material and ensure the orientation and position of the material. Next, we have included a spring platform as the perforating die as well as the lower pressure cushion for the blanking process. It is also for us to ease the ejector system for the scrap of the perforating process. The punch that we have used is not a regular punch, but is a beveled perforating punch with an inverted rooftop shear shape. This to reduce the force, noise, and as well as pressure in the perforating process to ensure a smoother process and as well as to lower the wear rate. Lastly, we also consider the ejection system for the end product after a breaking process, as we use a compressed air ejector system. From these two tables, we can see that a lot of materials has been included in the design of this equipment, in this machine, and it includes spring platform, spring breaking die, punching die, bottom die, the top die holder, as well as the ejector gas line. Respectively, get different materials like the D22 steel, the Inconga S750 as a spring material, as well as mild steel and aluminum has been used. From the color, we can see that all of them have different production process and need to be fabricated differently. The next process is the roll bending process. And from this part, we can see similarly the 2D drawings and the 3D CAD model of our roll bending machine design. And at the next slide, you can see the actual simulation of how our roll bending machines work, and you can have more details on the process of the roll bending. The roll bending process is bending the piece from the perforating and breaking process and making it into a bent aluminum piece like this. This is the final product after the roll bending process. As we can see, one of our design features is we included an orienter and feeder to accurately loading the material with the alignment and accurate alignment, and it is as well to prevent any tilted at the products, as the roll bending process is very important in terms of their alignment and other orientations. And the roll diameter of the top roll is always lesser than the product diameter to ensure a possible fit and a possible roll bending. We also included a counterweight at the end of the top strip roll to prevent the strip roll from toppling over while we unload the products. For the movement of the strip roll, we use the rack and pinion gear system, and spring supports are used for the mass of the top strip roll to reduce the force when we manipulate the height. So the gear and pinion system won't need to exert too much force to change the height. Next is we included all the bearings and different rotating joints like the strip rolls as well as the feeders. And we have also designed a system to remove the end product after it has been done from the roll bending process. Finally, this is all the parts included in the strip roll itself, design of strip roll itself, which include the bottom roller, top roller, the bearings, which is a standard part, the actuating holder, the gear, the spur, as well as the spring. And similarly, all of them have different material like aluminium and Inconga for the spring, and with different manufacturing process which are required. This is a continue of previous material list. So the second page is including the bearing holder, upper part and lower part, and this part of bearing holder can be opened, and the pin for the bearing holder as well as another gear, different size of gear. And their material and their manufacturing processes can be noted from here as well. Next is the material list for the orienter and the feeder. First is the feeder itself, and we use the bearing and the feeder roll with different materials and different manufacturing processes. Last but not least is the last process, the clinching process. From the clinching process, you can also see the 2D drawings and the 3D CAD model. So the next slide, similarly, you can observe the simulation of the clinching process itself. First, the material that has been gas being loaded into the clinching machine is the bent aluminium piece after the roll bending process. This is the one. And after the clinching, it has a clinch hole. Similarly to this illustration. Now we will move on to the clinching design features. First, we have included a point heated punch as well as a die to prevent the fracture of the metal sheet while clinching due to the sheet thickness is too small. The heating of the punch and die will be just a tiny point to increase the ductility at that particular point to reduce energy usage. We have as well designed a jig for the clinching point positioning, so the workpiece will be attached to a jig and be moved to each clinching point to have a consistent clinching point across all materials. Another design features is we have proposed the hydraulic actuation and wheels for the movement and control and jig, as well as we have included the rigs and cable ropes to support the force of the clinching process, as the clinching process itself needs a lot of force to be done. And the design and the patterns of the punch and the die are referred from the actual datasheet of the market product from a lot of references. Finally, we have moved on to the last part of the presentation, which are the materials included in the clinching machine. First is the stand, hook, wire rope, the punch, the die, and lastly is the ball bearing. And similarly, all of them have different materials and different manufacturing process, and you can see from the conclusion from this slide. This is the second part of the part list, and we can see another 5 parts, which are the wire of the die, wire of the punch, the wheel, the jig, and lastly the piston. The materials are including the wires, stainless steel 416, acetal, aluminium, and different manufacturing process to be done to each of them. So currently that's all for my part on the materials and the CAD design, and I will pass it forward to my teammate for further presentation. Thank you very much.
Now, this is the simulation of CNC machining on the parts of a manufacturing process. So in this video, certain part of the manufacturing process will show the animation. So this is the blanking die for the perforating and blanking process. And the time consuming for finished product is 87.667 minutes. Next, this is the bottom die, also in the perforating and blanking process. Total time consumed is 384.64 minutes. Next, this is the part in the 3-roll bending process. So for the bottom roller, the total time consumed is 392.459 minutes. And this is the part in the clinching process. For clinching die, the total time consumed is 5.761 minutes.
Finite element analysis. FEA is the process of simulating the behavior of a part or assembly under given conditions so that it can be assessed during the finite element method (FEM). Typical problems areas of interest include the traditional field of structural analysis, heat transfer, fluid flow, mass transport, and electromagnetic potential. These simulations, which are conducted via specialized software, allow engineers to locate potential problems in a design, including areas of tension and weak spots. FEA is the basis of modern software simulation software, with the results usually shown on a computer-generated color scale. FEA is focused on perforating and blanking process only. The punch pressed to the workpiece towards the die to form a blanking part. The material of workpiece: alloy steel. FEA is done on the perforating and blanking part. We take a look at finite element analysis result. This is the example of FE simulation. We can see that the stress is formed when the die is pressed onto the part. From the picture, we can see that the stress is occurred on the form part. From the color chart, red is the highest stress and blue is the lowest. High stress occurred on the form part is at the circular surface when it is pressed. The highest stress is recorded at 1.495. Same goes as the strain result. You can see that strain is being formed at the form part. From the color chart, red is the highest strain and blue is the lowest. High critical strain also occurred at the circular surface of the form part. The maximum strain value is 5.978 in power of negative 3. FEA helps accurately assess the stress and strain that occurred in the form part. The findings are shown in the picture with Gaussian color gradient that S is the study of physical stress behavior. Based on the result obtained, the highest stress is recorded at 1.495 epsilon power of negative 2 Nm second, and the maximum strain value is 5.978 epsilon negative power of negative 3. It is found that high stress and strain is formed when punch is pressed on the part formed. This is because the force generated by the punch is only applied on the area of perforating and breaking.
First off, we have this CNC milling machine that we suggest, and then this is the conventional milling machine. So these are the parts for fabrication, basically the parts that we will fabricate ourselves. Then we have the standard parts. As for other parts like workbench and spring platform, we chose to outsource it, or basically just go for external vendors instead. Next, we have the cost of fabricating parts like the blanking die, the bottom die, as well as this punch die, and these top die holder as well, and of course the ejector gas line. The difference between the ejector gas line and the rest is that it uses conventional milling machine instead of CNC. The total cost for the perforating and blanking process basically includes the parts for the fabrication, the standard parts, and the other parts like the workbench and the spring platform.